Hello, this is Andy Schweitzer, a little video on some of the individual aspects of determining the voltage at what we call non-standard conditions, meaning that we've changed our temperature and we've changed our concentrations, so our voltage is changing as well, and how we might figure that out. This first little slide here you're looking at is pretty standard reaction. We did this in class to some extent. We have copper metal reacting with silver nitrate and produces copper nitrate and silver. So this is just standard chemical reaction. I have the copper being oxidized with 2 electrons being given away to the reducing material. They pick up, in this case, 1 electron, so it has to happen twice. Pick up both electrons. This has a reduction potential of 0.8. This has a oxidation potential of -0.34 volts. Alright, so this gives us an overall reaction of 0.46 volts, which means the reaction will run spontaneously. I could take a piece of copper metal and drop it right into this solution, and the reaction would exchange electrons, and I would have copper 2+ ions produced and silver metal produced out of solution immediately. I, however, can set up a little galvanic cell like this, and this is brushing over material that we've already covered in previous videos and in class. Either way, set up a little galvanic cell. The copper jumps off into solution. Every time 1 copper jumps off, 2 silvers have to jump onto the solution, onto the post, forming a solid. Over the course of the reaction, I lose reactants and I gain products. So my copper metal plus my silver ions, 2 of them, go on to produce copper 2+ ions and silver metal. So over the course of the reaction, okay, I have, well, I start out initially fully concentrated, okay. We got a 0.46 volt reaction. What does this mean? Well, this is called my electropotential at standard conditions. That little circle there, degree sign, means standard, or STP. That means this concentration starts out at 1 molar, this concentration starts out at 1 molar. This and this are solids, they don't have concentrations. So as the reaction proceeds, this concentration starts to go down, this one starts to go up, so I start to have concentrations of copper ions in here, and the silver is more and more of the silvers are jumping onto the post, so I have less and less silver. As this process occurs, the voltage starts to dwindle, down, down, down. This goes down, down, down. This goes up, up, up. And eventually my voltage gets to 0. And my reaction, or my battery, appears to be dead. In reality, we've just achieved what's called equilibrium. So, in order to keep some of the variables constant, to give everyone an even playing field to know what we're talking about, we have this STP, which means essentially 1 molar concentration, and it also means 25 degrees Celsius. Okay. So the point of this video is to try and get a better understanding of what it means to alter these conditions of concentration and temperature. Okay. Now, in the AP exam, I will tell you that altering concentrations in the past years has been very common. Okay, they will say, okay, with these new concentrations, what's my new voltage? That's very common. Now, for temperature-wise, it just hasn't been something that's been tested. They don't say, if I crank my temperature up to 50 degrees, what's my new voltage? It just isn't something that I've seen. There are 2 aspects, therefore, of this. Okay, one is qualitatively. If I drop this, increase this, if I alter these concentrations vaguely, what's going to be the general increase or decrease of my voltage? Okay. Now I'm going to talk just a minute or so about that involving concentration. You should understand that if the concentration of my reactant, okay, if I increase the concentration of that, my voltage will, in this case, increase. Okay, more stuff that can attempt to roll the product. If I were to decrease, let's say, increase the concentration of my products, okay, that will cause a drop in my voltage. That's where I'm going to eventually in the end, where I crank up those concentrations. In this case, if I were to just the opposite, my reactant concentration were to drop, my voltage would drop. If I were to drop the concentration of my products, my voltage would, in this case, increase. Okay. So, in other words, just to highlight this again, is that as the reaction proceeds, I'm sort of rolling downhill, taking away here and producing here. So, the more of this I have, the more I can roll down, and the bigger the hill to roll down, the less of this I have, the more steep it is. Okay. If I want to have max voltage, in this case, if I want to maximize my voltage, I want to increase the concentration of my reactants, and I want to decrease the concentration of my products. Okay. Now keep in mind that this reaction is just going to equilibrium, which is, in this case, would be described as being Q or K. K is the end point. Okay. I always use a little picture like this, reactants going to products, and eventually you'll get to a point where your concentration of your reactants and concentration of your products get to some balance point called K. And of course, as I drag myself off of this point, okay, changing the concentration of reactants, changing the concentration of products, I get a Q point, and eventually it rotates back. Okay. The more I increase these concentrations, the farther I pull this off of my equilibrium constant, okay, my equilibrium ratio. So you should have understanding just generally, okay, if I increase the concentration of my reactant, I will increase my voltage. If I decrease the concentration of my reactant, I will drop my voltage. If my product, just the opposite. If I drop my concentration, my voltage increases. If I increase the concentration, my voltage drops. Okay. Now, you can actually mathematically calculate the exact voltage with what's called the Nernst equation. And we will look at that in a moment. Temperature-wise, like I said, isn't something that is generally very well tested. Okay, there are ways of calculating it, but as a general rule, you should understand that in your car battery, for example, at very low temperatures, it just simply doesn't work as well. The chemical reactions aren't working, they aren't happening. So at low temperatures, I get low voltages. At high temperatures, I'm getting high voltages. We'll see more about that in a moment. All right, so as we look at this a little closer, a few things you want to keep in mind. Reactants, concentration, product concentration. I often look at right down the middle here is where I draw what I call STP, where your concentration of your reactants equals the concentration of your products equals 1 molar. Let's just say hypothetically, and your end point or equilibrium point is right here. At this point, your K, you're at K. Okay. As your battery runs down, it runs to this point. At this point, your voltage equals 0. Nothing's happening anymore. So what happens when I change my concentrations? Okay, well, I crank up to 1 molar. This is referring, this STP, the 0.46 volts, is referring to at this point where my concentrations are 1 and 1. We call this the electropotential standard. Again, that is standard temperature and pressure. If I were to go outside that range, I should understand that as I pull farther and farther and farther away from my equilibrium point, more and more energy is being stored. At this point, I have larger amount of concentrations. Okay, I have of reactant concentrations, even less and less amounts of product concentration. I'm getting farther and farther away from K equals the concentration of my products or the concentration of my reactants. My fraction is getting farther and farther and farther and farther away. In fact, when I recalculate this value at this point or at this point, we call it Q. Q is just that same calculation, it's just non-standard. We're not at equilibrium. You should expect you to have your voltage, your electrical potential to increase as you're getting farther and farther away. Your electrical potential voltage is cranking up higher and higher as you stretch this thing out more and more and more. Again, then as you let the reaction run, it runs down, 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 down. Eventually, your electrical potential equals 0. Same thing as your voltage. Another example of this, how you might describe this, is what's called Gibbs free energy. This is a topic that will be covered usually during thermodynamics. We covered in regular chemistry, something that think about it, you may remember from previous chemistry or whatever. In this case, a negative delta G means that given an opportunity, this thing will run from reactants to products. So it is what we call product favored. It means that the spring is loaded and it's ready to go. If I go delta G prime, that means, okay, at standard conditions, which again is right here, what's my delta G at this point? Well, if we're right here and my K is right here, my ending point, this would give me as I again wind it out, okay, I would have a negative delta G, means I'm flowing from reactants to products. Flowing in this, given an opportunity, I'll flow back towards this point. As I change my concentrations to get farther and farther and farther away from my end point, my equilibrium point, my delta G becomes more and more and more negative. Okay. I can only call it standard right here when it's at this point. My delta G at this point would not have a standard sign, but it would have a value of more and more and more negative, increasingly more negative. As it unwinds, coming towards the end point, get to equilibrium, my delta G also would equal 0. So when I get to this point, delta G equals 0. It would not have a standard prime sign because it's no longer there. So standard prime means that's where I currently am at, and take the standard off. The standard prime sign means I'm right here, right at my STP, but take this prime off, that's my current location, whether I'm over here, whether I'm at equilibrium. Okay. Now, if I want to actually know the actual voltage at various points, okay, I can calculate that. That's called the Nernst equation. Okay. Now, the Nernst equation looks like this. Okay. I will just happen to mention to you that the Nernst equation, as of 2014, has been removed from the advanced placement exam curriculum. So I'm going to walk through this, but they're never, at this point, as far as I know, they're not going to have you calculate off this. I do believe you should be able to conceptually know if my voltage is increasing or decreasing, okay, based off some of the topics we've talked about here. You should understand the relative position of standard pressure versus equilibrium and know whether my voltage is increasing or decreasing. Mathematically, you can calculate it. So here's how that works, okay? These are both the same equation, just different looks at it, okay? There's also a log version of this thing here, okay? I like the log version because some kids are just easier at conceptually understanding the log system versus natural log system, which makes sense. But it is going to be E cell. Now, there's no prime here, so this is my current location of where I currently am based on the current conditions that I'm provided. This is E cell prime. That's my standard prime at a standard location. Will never change. That's your standard cell STP cell voltage. For our purposes now it's 0.46 volts. the reaction could run down to 0, and then my standard E cell is going to be 0. The reaction could run out. This thing's still 0.46 because that's not where I currently am at. That's your hypothetical STP conditions. Minus RT over Faraday's constant. R is a universal gas constant. This is temperature. And usually it's 298 for standard temperature and pressure. Now this is going to be multiplied times the natural log of my Q. Okay, now let's just say hypothetically that my standard STP, okay, is 1 molar concentrations. So for my chemical reaction that I just ran with copper and with silver, I'm going to rewrite that out here. Okay. My reaction is this: copper metal plus silver plus ions yields copper 2 plus ions plus silver. Okay. This is going to be a 2 and a 2 just in order to keep my electrons balanced. My copper concentration here is zilch. It doesn't have a concentration. This guy is 1 molar. This guy here is 1 molar. And this one, again, doesn't have a concentration. Let's plug these values into this guy right here. Okay, I'm going to run this thing through entirely right below here. So equals 0.46 volts minus, and I'm going to take this whole thing here, 8.31, which is my R value, and then times 298, okay, over Faraday's constant, which is 96,500. Now, multiplied by the natural log of my Q. My Q is my ratio of products over reactants. So my Q in this reaction is 1 molar divided by 1 molar. The concentration of my copper 2 plus ions over the concentration of my silver ions. Now, one important aspect here is to realize that because there's a 2 here and a 2 here, I get a square here. Equals 1 divided by 1 squared. 1 divided by 1 squared is still going to go 1. Plug that value in here. The natural log of 1 equals 0. 0 times all of this stuff equals 0. So in the end, if I plug in STP or standard conditions into this guy, it's going to be 0.46 volts minus 0 equals 0.46 volts. So if I plug standard conditions in, I should get my standard voltage, which is what I got. Okay. If I plug in other conditions into my Q, different concentrations here, like if I were to crank this up to 2 and this to 0.5, I would see different voltage appearing. Before we wrap this up, let's run through a typical question that you might see on an advanced physics exam. And I just sketched out a very simple cell. Looks like a third grader drew it. But the question would ask, we'd say this. Okay, what would happen if I added 50 milliliters of water to both of these cells, this one and to this one? So I've now diluted the concentration of the ions. Okay. Two different options which I'd like to answer this question at. Okay. Now we don't know the concentrations, and they often don't tell you the concentrations, and quite frankly, for the rest of this year, as far as how, since they've sort of eliminated the Nernst as an equation option, it's going to be qualitative at this point. But two different types of reactions. Let's say this one, for example, we have copper metal plus zinc 2 plus yields copper 2 plus zinc metal. That's one option. And in this case, I have copper metal plus silver plus ions yields copper 2 plus silver metal. Okay. This is a concentration. Okay, so how would these things be affected? Now, when I run this through here, I can simply look at the Nernst equation and say, okay, well, my standard cell potential, my current cell potential is equal to the cell potential of the standard minus RT divided by Faraday's constant times the natural log of my Q value. Of course, when Q gets equilibrium, Q actually becomes K, just to keep that in mind. and then our voltage is going to be 0. But either way, my current voltage would then be 0. But either way, let's look at these guys. So for this one, my Q would be equal to the concentration of my products. In this case, that product, I'm just going to erase that for a second. My product is going to be the copper 2 plus ion. And then this guy is the concentration of my zinc 2 plus ion. Alright, so in this one, you should note that this is being the product right here. This is my reactant. You should note that if this thing increases, my voltage will increase, and vice versa for the other guy. So this guy were to drop, then my voltage would increase. But in this case, we are going to add water to both sides. So I have, let's say, 1 molar and 1 molar would give me a Q of equaling 1. If I add water to both sides, let's say I drop to 0.5 divided by 0.5, my Q still equals 1. So for this reaction where my coefficients are 1, 1, 1, and 1, this reaction, adding water to both sides, has no effect on the voltage. That's important. Okay. Now in this one over here, I have my Q equals the concentration of my product copper 2 plus ion over the concentration of the silver plus ion here. This is my product, this is my reactant. You should note that increasing this value, okay, will increase the voltage, just hypothetically. But in this one, because there's a 2 here, okay, I get a square here. So 1 divided by 1, standard conditions, this is squared, equals 1, just like this standard condition equals 1. But if I were to drop this to 0.5 and 0.5, all right, over 0.5 squared, this gives me 0.5 over 0.25, sorry, okay? This is changing now, so if I have coefficients, this is going to have some kind of an effect, okay? So in this case, this becomes 0.5 over 0.25. In this case, that equals 2. All right. Let's just walk this through on the nearest equation and see how this is going to have an effect on our chemical reaction. Okay. The E cell for this reaction is 0.46 volts minus 8.31 times my temperature, which is 298, over my Faraday's constant, which is 96,500, times my natural log of 2. Now, the natural log of 2 is a pretty common number, actually, for chemists, nuclear chemists especially. This is going to give me a positive value of 0.693. All right, so in this case, let's just run the math through. 0.46 and then minus, I'm going to put all those values together. I have 8.31 times 298 divided by 96,500 equals, this is going to be a negative, all right, 0.02, so I'm going to go 0.0256 multiplied times 0.693. All right, so those order of operations wise, we'll do those first. All right, so it's going to be in this case that value times 0.693, and I get a negative 0.46 minus a negative 0.0177, and in this case it is subtracting, so we will get a smaller voltage, 0.46 minus that previous answer, and not a whole lot at this point, but it's 0.44 volts. All right, so Interesting problem, pretty common.